All right. Hi there, guys. My name is Wilfrid, and I'm a senior math tutor. And I'll be bringing you guys through 10 questions today about functions and algebra. And yeah, that's pretty much it. So a little bit backstory upon myself. I graduated from a master with a major in biochemistry and a minor in mathematics. And these questions that I'm doing is based off of one class. If you have any other problems with your questions or any issues with concepts or anything like that, please submit them to one class and we'll get to them as soon as possible. So other than that, let's begin. All right, so the first question reads, find the minimum value of the function y equals x squared minus 3x plus 2. So as I've been teaching previously, so we first identify this function as a quadratic function. We notice that because it is of the standard form, y equals ax squared plus bx plus c. Okay, so it's of the standard form ax squared plus bx plus c. And we know if we graph our quadratic functions, this is what they look like. So they have two primary orientations. They can either have a upward facing orientation or a downward facing orientation. So when they ask us to find the minimum value of the vertex, in other words, they're asking us to find the vertex of the function itself. And the vertex of the function is either the max value or the minimum value, dependent on the orientation of our parabolas. So these are what we call vertices, okay, or the vertex, okay? So there's two ways to do this. Well, essentially, there's actually three ways. The first way is that you can graph your parabola, and you can visually locate where the minimum value is. The second way is that you guys can calculate the coordinates of the vertex by first finding the x coordinate of the vertex, and that's given by this equation here. So x vertex equals b squared minus 4ac, or sorry, b over 4a. I think it's 2a. So you guys can do that. Or the third way is actually just to calculate it straight up by using this formula here. So min slash max is given by this formula, okay? C minus b squared divided by 4a. Okay, so you can use a visual graph to locate the min-max, use the x vertex, use the coordinate formula to find the x coordinate of the vertex and calculate for the y, or just use this simple equation to just find the y coordinate of the vertex. So we're going to be using this, and that's what the junior tutor also did. So here in our problem, we have our quadratic equation of form in the standard form of y equals x squared minus 3x plus 2. So we know that a is equal to 1, the coefficient, b is equal to -3, and c is equal to 2. So if we're going to plug that into our equation here, we have min equals 2 minus -3 squared divided by 4. Okay, and that equals 2 minus 9 over 4, and that equals to be 1 over 4. Negative. Okay, so that's the min value of our function x squared minus 3x plus 2. And if we were to graph it, we can visually locate that, yes, indeed, it is -1 over 4. Okay, so that is how you do this question. And there's three ways of doing it. First, by visually graphing it. Second, by finding the x coordinate and then subbing it into your quadratic equation. Or the third way is just to calculate it straight outright using this equation, c minus b squared over 4a. Okay, so this solution is correct. Good work. Okay, let's move on. All right, question number 2. How do you find the domain and range of a rational function? So in my previous lectures or sessions, I covered what the domain and what the range of a function was, and I'll repeat it again. Okay, so let's say that we have a pool or a value of x values here, okay? So out of all the real numbers, we have a pool of x values. Okay, we'll say this is x. All right, and let's say that we have a pool of y values called, let's just call it f of x. Okay, so the domain is every value of x that defines the function. Okay, so a function's primary purpose is to map one value to another through a set of rules, a set of axioms, or by a function kind of thing, right? So the domain is all the values of x that define f of x. Okay, so all the values of x that lead to f of x. So these values of x can be the whole real number set, it can be the integer set, it can be the natural number set, it can be expansive or very, very exclusive, depending on what our function is and what our function is describing. Okay, so we call this bubble, this red bubble, the domain. Okay, so from the domain through the function f to f of x, we have what we call the range, which is all the possible values of f of x of the function itself, and we call this the range. Okay. So the way that we usually find the domain of our function is by finding all the cases of x or all the values of x which do not define the function itself. And by doing so, we can write a concluding statement which will encapsulate the domain and exclude the ones that are not part of the domain. And there's a very neat trick of finding the range. Okay, so you guys can also think about finding the domain and range by graphing them visually and looking at the graph and saying where are some discontinuities, where is the graph leading, and what parts of the graph are excluded, right? So finding the range, you can just look at a graph and be like, oh, I see that this whole function is positive. That means the range is all f of all y greater than 0, right? You can say that. Another way to find the range is by finding the inverse function. Okay. Oh, that's blue. So by finding the inverse function, what's very neat about the inverse function is that the range of the original function becomes the domain of the inverse, and the domain of the original function becomes a range. So by finding the inverse function and figuring out its domain, we can find the range of the original function. Sometimes it's hard to find the range because you can't graph out the whole function itself, and most of the time we can't really figure out where f of x doesn't exist, I guess you could say. All right, so we're going to use this trick to solving this problem. So now let's address the problem itself. So how do you find the domain and range of a rational function? Okay, so if you were to graph out a rational function, this is what it would look like. And I'm just going to do a general view of the rational function here. So let's say that, oh, it's in gray for some reason. Okay. Let's say that this is x and the y-axis. So rational functions kind of look like this. Okay, so they have two sides of them, and they look like this. Okay, so there are parts of this graph where it's undefined. Okay, and we're going to try to figure that out mathematically speaking. Okay, so the junior tutor wrote here that a rational function is defined as a rational fraction where both the numerator and denominator contains polynomials. So that is technically correct. So we have, let's say, big f of x is basically the ratio of two functions. So f of x over g of x. Okay, and these functions can be whatever you want. Okay, in this particular example, the junior tutor said polynomials functions, and for a large majority of the mathematics you'll find in high school math, it's going to probably be polynomials. So we're going to stick with polynomials for now. Okay. So for a fraction, it is undefined when the denominator is equal to 0. So in an original fraction with just numbers, you can't divide stuff by 0, and that is a issue due to the limit of that, I guess, number. But in the function, it's the same thing. So when you have a rational function where the denominator is equal to 0, the limit is undefined, and that is a function of how limits exist and how limits work. I won't be getting into too much detail about that, but that's a key to figuring out the domain of our function here. So the junior tutor says With that in mind, when the denominator is equal to 0, it is undefined. The domain of a rational function is a set of all real numbers that make the denominator non-zero. So to find the domain of a rational function, we have to figure out the cases where the rational function, the denominator of it, is equal to 0. So that's the key to this, okay? So then also the junior tutor expands, saying the range of a rational function can be found by graphing the function or by finding domain of the inverse function of the graph, okay? And then the junior tutor uses an example, and we'll go through the example now. All right, so the example here is that we have f of x. Okay, ignore this. This is just an example of this. Okay, so let me just draw another line here. Okay, so f of x equals x minus x squared minus 4. Okay, so we're going to find the cases where the denominator is equal to 0, and that will help us find our domain. Okay, because the domain of a rational function is all the real numbers except where the denominator equals 0. Okay, so to find the domain, we need to set the denominator equal to 0. Okay, so we're going to say set denom. All right, this is a short form to equal to 0. Okay, so we have x squared minus 4 equals 0. And we're going to do a quick factoring here. So it's x plus 2 times x minus 2. Great, equal to 0. So we have two values of x that will make our denominator equal to 0, which is plus 2 and minus 2. All right, great. So now we know the values of x that will make our denominator equal 0. So now what is our domain? So our domain is going to be x belonging to all real numbers except for x cannot equal -2 or +2. Okay, so that's going to be our domain. So we realize the fact that the rational function here, this is not the graph of this particular function, it exists on all real numbers except for when the rational or the denominator equals to 0. So in this case here, where the junior tutor wrote, when x equals -2 or +2, you see here that the function from leading from the left side or the right side is going to positive infinity. But the function leading from the left side approaching -2 is going towards negative infinity. So this is where we have an undefined value here. And the same with this one here too. Okay, so the range, we're going to do the range too here. So to find the range, we're going to do the inverse function here. So we're going to switch x and y. So x equals y squared minus 4. I'm looking at this already, and this is going to be a mess to actually isolate for y. So we're going to take the visual method again, and we're going to look at our graph here provided by our junior tutor. And the reason why this is hard to isolate for y is that we have to get rid of this rational function first, and it's going to be a whole, it's going to be very difficult for us to do that. So we're just going to use a graph, and we're just going to visually identify what the range is, okay? So our range is from -infinity to -2 here. So you can see here that at -2, there is no value here. So our range is -infinity to -2, -2 to 2, and 2 to positive infinity. So in fact, the range would just be -infinity to positive infinity. Yeah. Our asymptotes x equals positive -2. Thus, our range will be from -infinity to -2. Okay, so there's an issue with the statement here. So the range would actually be from -infinity to infinity. And that's because you can see here that the range is measuring what are the possible values of y, and we can see here that this graph is always going to be trending from negative infinity to positive infinity up here, right? And it's also going to be close to 0 too, so it's the whole real value here. I don't know what she means or what they mean by this, but I do not think this is correct actually. Because if we visually evaluate this graph here, we can see that the range spans from negative infinity to positive infinity, and it also spans near the decimal point numbers too here. So the range would actually just be all the real numbers. So actually this solution is partially correct. So yeah, my last comment for this is that you guys can try to isolate for this and try to find y inverse and try to find the domain. It's very difficult to find that, but I would suggest looking at the graph itself and evaluating what the range is from the graph. All right. Okay. So let's move on to the third question here. So the third question reads, find the zeros of the function f of x equals x squared minus 8x minus 9. So when they tell us to find the zeros, they're asking us to find the solutions for this equation here. So find the zeros is the same thing as saying find the solutions to x squared minus 8x minus 9 equal to 0. So that's what they mean by finding the zeros. So it's basically saying find the values of x that will make this equation equal to 0. Okay, so yet again, you guys can apply the visual method of locating where the graph is equal to 0 and finding those points manually. Or you guys can use factoring or the quadratic formula to find the zeros. And in this case, we're going to use factoring. Okay, so we're going to set our equation out first. So let's f of x equal to 0. So that means that x squared minus 8x minus 9 equals 0. All right, so we're going to use our cross multiplication method, and I'm just going to briefly cover that. So the factors of x squared are 1 and 1, and the factors of 9 could be 3 and 3 or 9 and 1. We're going to use 9 and 1. And since it's a negative number, we're going to use negative 9 and 1. By cross multiplying, we get negative 9 plus 1, which is equal to negative 8. So we've found our factors, which is x minus 9 and x plus 1 equals 0. Okay, that means x equals 9 or negative 1. Okay, so we have found our zeros, which is x equals 9 and x equals negative 1. You guys can check these values by plugging it back to our function here. So let's say let's x equals 9, then that means f of x is equal to 81 minus 72 minus 9, which is 81 minus 81, which is 0. So that is our first zero. And let's x equal negative 1, and we get f of x equal 1 plus 8 minus 9, and that equals 0. So we found our zeros, which are the solutions to the equation x squared or f of x equal to 0. Yep, so the solution is correct. All right, moving on to question number 4. All right, so the half-life of phosphorus 32 is 14.26 days. Calculate its decay constant. So when we're talking about half-life, we're talking about basically the, the the decay of a certain material. So I spelled half-life wrong. Okay, so basically the half-life is a measure of time, which helps us understand how fast or how slow a substance decays, and it's measured by um, measuring how fast it takes a substance to decay to 50% of its capacity, right? So, for example, if we had substance A, for example, right, and we weighed it out and we know it's 100%, right? So the half-life is the measure of time it takes to have this substance decay to 50% of itself. So this is what a half-life is, okay? And the notation for it is T with the half in the subscript here, and that helps us to denote that as a half-life. So usually this is applied to radioactive materials and unstable isotopes, for example, because they take a certain amount of time to decay. And by measuring out its half-life, we can have very useful applications such as carbon dating, or by understanding how effective a pharmaceutical is. So a half-life is very important for that kind of stuff. So let me just write out that definition here. So the half-life can be calculated by dividing ln of 2 divided by what we call the decay constant. So this decay constant is what basically determines how fast or how slow a half-life is. Okay. So in this case, we know that phosphorus 32, the half-life of it is 14.26 days, right? So what we're given here is T of half equals 14.26 days. All right. So if we want to calculate the decay constant, we need to plug it into our equation here. So 14.26, I'm not going to include the units here, equals ln 2 divided by k. So we have k equals ln 2 divided by 14.26. Okay, that makes sense. So the decay constant is going to be 0.0486, and it's going to, the unit of the decay constant is going to be whatever it takes to cancel out this. So since ln of 2 doesn't have any units, and this has a unit of days, when we're isolating for k, we have to be worried to get rid of these units here. So k is going to be days inversed. So yeah. So per day, so this basically means the decay constant means that the substance per day decays 0.0486 of itself. Or if I were to times that by 100, it would be like 4.9% of itself. It loses 4.9% of itself per day. So that's what the decay constant tells us here. Okay. So why I included this question in the in my session today? This is more of a chemistry question. It has something to do with the function itself, right? Because we know the logarithmic function is basically is the inverse of our exponential function, and it has. So I just wanted to connect the relation between mathematics and chemistry here, and I thought it was also a cool question because it was included in the mathematics session for some reason. So anyway, so that's how you calculate the K constant. And the half-life of any material is the time it takes for a substance at 100% capacity to decay to 50% of itself. And one more thing to note before I even end is that if we extrapolate from this diagram more, so if say we have substance A, and we go through two half-lives, so the second half-life is going to be 1/4 of A. The way half-life works is that it's the time it takes for the current state of the substance to decay to halfway. So if you can extrapolate from here, a quarter of a substance, if you go through a third half-life, is 1/8 of itself. And that's a function of the exponential function itself, right? The smaller the substance, the less it decreases. But that's the last thing I want to note about that. There's a trick, or there might be a trick where like you think, oh, after the second half-life, it's going to decay to 0, but it's always half of its current state. Okay. So in theory, this will never decrease to 0. It will decrease to very, very minimal amounts, but it will keep going. It'll just keep going. Anyway, that's my spiel on that. So this solution is correct. Let me just check the math real quick here, just to make sure that nothing is sketch. So 0.3, so 1 of 2. Okay, that equals that, divided by 14.86, or 26. Yeah, so he rounded to 4 decimal places, which is correct. Okay, so that's correct. All right, moving along to question number 5. All right, so back to regular math. Let me just say this solution is correct. Good work. So the next question reads, a line has a slope of -4 and passes through the point 0 and -5. What is the equation of the line? So they give us 2 pieces of information here, the slope and the point where the line passes through. So I'll be going through 2 different methods of calculating this. I've been through this before, but I'll do it again. So the first method is by just using the standard equation of a line and going from there. The second method is by using the point slope formula and going from there. Okay, so the standard equation of a line is y equals mx plus b. It could be plus or minus b, doesn't really matter. M is the slope, b is your y-intercept, x is the independent variable, and y is the dependent variable. So here they've given us the slope and a point that passes through the line, so this is very easy for us. So we already know that m equals -4. So let's plug that in. So if that at m equals -4, then we get y equals -4x plus b. All right, cool. So now we're given a point on the line. So let's just say sub 0, -5. And what do we get? So -5, -4 times 0 is 0 plus b. And now we know that b equals -5. And now we have found our line equation, which is just y equals -4x minus 5. Cool. So that's the first method of calculating or finding your line equation. All right. The second part is by using the point slope formula, which is y minus y naught equals the slope times x minus x naught, where y naught, x naught is our point that we know of. Okay. So we're given m, which is -4, and we're also given x naught, y naught, which is 0, -5. All right, cool. So let's plug in all this information here. So y is plus 5, m equals -4, x minus 0. And what we get here, we get y plus 5 equals -4x. So we're going to isolate for our variables here. So we're going to move this to the other side. So we're going to do y plus 5 plus 4x minus 5. And we're going to do minus 4x minus 5 plus 4x. Cancel, cancel. And we get y plus 4x equals -5. Wait a second. I need to move it back. Why did I do that? So if I just reverse this, it'll just be here. I'll move it back. Y plus 4x minus 4x equals -5 minus 4x, which equals y equals -4x minus 5. So we can see from these two solutions that we have the same solution. Another thing to note, looking at our graph here, is that we have a negative sloping function with an intercept at -5, and so now we can graph our line. So those are two different ways of calculating your equation of a line from two pieces of information. You can choose which one you prefer. And also, just one more thing to note before I move on to the next question is that there can be different pieces of information that you're given. For example, you can be given 2 points on the line. You can be given the y-intercept, x-intercept. It's all up to how, but even though you're given different pieces of information, you can still use these two methods to calculate the line of the equation of the line, regardless of what kind of information you're given. Okay, so this solution is correct. Nice stuff. Cool. All right, question number 6. All right, so we're moving on to what we call compositional functions. So the question reads, how do you find f of g of x and g of f of x given f of x equals 2x minus 3 and g of x equals x squared minus 2x? So I talked about domain and ranges of functions. So I'm going to describe what the compositional function looks like, okay? All right, so we have our original x, okay? So independently, these two functions can act in different ways. So let's say that, actually, let me write real value numbers. Okay, this is just an illustration for now. Okay, so independently, these two functions can take x's from the real number set, and it can lead it to different places. So this is g, this is f, and we have the range of g of x, and we have range of f of x. Okay. So like in my previous illustration, the domain and range, I've already described that. So independently, these two functions work, right? So they take values. So this is the real number set, right? I just didn't draw, I guess a better accurate drawing of this in this context would be like a Venn diagram kind of thing, where colors, where we have like the domain of G and the domain of F, where they share values entirely, but they can also not share values, right? This is the Venn diagram. So let's just denote these as like x of G and f of G, x of F, okay? This is how you don't really write it, but I want to illustrate this entirely, okay? All right, so you have the domain, right? So these functions can work independently. But when you have a compositional function, it looks more like this, okay? So it really does matter which way how you read it. So in this way, we read f of g, right? So that means that g of x is the function within function f, and this is what it looks like, okay? So let's say that we have a pool of x's, and so we have the domain of G. Okay, so this is a domain of G of x. Okay, so we have the domain of G of x, which is I'll just label it x. Okay, and a compositional function works by applying the function g first and producing what we have as the range of g. Why is this happening? And the range of g is g of x. Okay, so I'll denote this as g of x. All right, range of g of x. So let's say that the range of g of x is the middleman or the domain that's going to be acted out for the function of f. Okay, so that means that function f takes the valid values of g of x, and it uses that to produce its own values. Okay, so f, and it produces what we have here as f of x. which is the range of f of x. Okay, so that's how a compositional function works, and I'm going to label this as f of g. Okay, if it was g of f, then it will be switched, right? So we'll have the domain of f first, applying function f to go to the range of f, and using the range of f values to apply the domain for function g to produce the range of g of x. Okay, now in our particular example here, we have polynomial functions. So we know that the whole real number set is valid for the domain for both, right? But in a general case, there are some compositional functions where the final range of f of g of x is not going to be the same as the range of f of x independently. And that is determined by by the domains of the specific functions itself. Because sometimes your function g may produce values where does not fit into the domain of f. Okay, and because of f of g of x, sorry, and because of that, they have to be excluded from the pool of values for the domain of f of g. Okay, but that's super complicated stuff. In this case, we have polynomial functions, so we're just going to assume that everything is up for grabs here. Okay. So let's calculate f of g, and then let's calculate g of f. Okay. So how I like to write this out is when we say f of g of x, I like to write it out. So we see here that the g function is the one that's within the f function. Okay. So we're going to write out the f function first. So the f function is 2x minus 3. So I'm just going to leave a gap here. So I'm just going to leave a bracket here for now, minus 3. Okay, and this bracket is where g of x is going to be. Okay, so we can write g of x. So this is equal to 2 times, so f of g of x is 2 times g of x minus 3. So now that we have established that, we can just sub in g of x, right? So that's going to be 2 times x squared minus 2x bracket minus 3. And if we were to expand that, we would get 2x squared minus 4x minus 3. So we see here now that we have gotten a quadratic function from the compositional function f of g of x. Okay, cool. What if we did it the other way around? Okay, so now f is the inside function, so we're going to sub it into our g of x. Okay, so g of f of x, what is that going to be? So we see here that we have a bracket here for this, x squared minus 2 times the bracket. And we're going to put our f's in here, okay? And if we put our f's in here, we get f of x squared minus 2 times f of x. So we see here that g of f of x is basically f of x squared minus 2 times f of x, okay? If we were to sub that in together, we get 2x minus 3 squared minus 2 times 2x minus 3. If we were to expand this first term, we would get 4x squared minus 24x plus 9. And we'll expand this, and we get minus 4x plus 12. And if we were to simplify, we get 4x squared minus 28x plus 21. Cool. So we also got a quadratic function here. So these are the two compositional functions, and they have their own domains and ranges. Okay. So last thing to note, the domain of f of g of x is going to be the domain of g of x. Okay, and the range is going to be the valid values of f of x, of f of g of x at the end. Okay, so that might exclude some values that are that define independently g of x, but when you do f of g of x, it doesn't make it define anymore. Okay, and we'll be covering that a little bit further as we go along. But for now, we can move along. Okay. Did I expand wrong? G of f of x. Hold up here a second. So g of f of x, 2x. they added wrong, I believe. I also added wrong. This should be 12. And this should be 16. Sorry about that. Did I add anything else wrong here? So 2x squared negative 12x plus 3. Why did I write? Okay, sorry guys. I'm a little bit. I'm making a lot of silly mistakes today. It should be 6. This should be 15. All right. Hopefully I didn't make any more mistakes. 4x squared minus 16 plus 15. I think I'm good. So here the junior tutor forgot to write out the last term. They didn't include the 9 here, so that's why they have a 6 instead of a 15. So for the solution is almost correct for your g of f of x. You expanded the 2x minus 3 squared term incorrectly. And I almost expanded it incorrectly. That's why you always double check your work, guys. All right. All right, so we talked about compositional functions, and now we're going to talk about a different function. So another thing you can do with functions is that you can add them, subtract them, multiply them together, and you can create a totally different function. So in this case, we have f of x equals 3x squared plus 1, and g of x equals 1 minus x. So what is the value of f minus g? So if we were to have f of x equal 3x squared plus 1, and g of x equals 1 minus x, then f of x minus g of x would be 3x squared minus plus 1 minus 1 minus x. Okay, and that gives us 3x squared plus x. Nope, plus 2. No, yeah, we're good. All right, so that's how you find the f minus g portion, and then we're going to plug it in. So now that we have f minus g of x, which is 3x squared plus x, we're going to plug in 2 here. So f of minus g of 2 equals 4 times 3 equals 12 plus 2, which is equal to 14. Hopefully I didn't do that one. Yeah. So that's another cool thing that you can do with functions. You can subtract them, multiply them, divide them by each other, and they all come with a different set of rules, right? We were talking about rational functions earlier, right? So if you're dividing something and you can't simplify the denominator, then the domain of that function changes, right? So that's exactly what we're going to encounter next, especially with compositional functions like this. So let me just write out the comment for this. So the solution is correct. So basically, before I go on to the next question, I just subtracted the general function for both from each other, and thankfully they came up with a polynomial function, and we just plugged in 2 to find the value of this function, which is just a quadratic function. So this solution is correct. Work. Okay, so here we go. So all that talk about the domain might be different for a compositional function and in comparison to the domain of the independent functions itself. We're going to apply that here. Okay, so the question reads, if f of x equals x minus 3 divided by x and g of x equals 5x minus 4, what is the domain of f of g of x? Okay, so we see here that the domain, so if we have f of x, right, of x minus 3 divided by x, we see here that the domain of this function is x belongs to all real values except x cannot equal to 0. Okay, So that's the domain of our first function independently. The second domain, right, g of x equals 5x minus 4. The domain for this is x belongs to all real values. But as you see, when we do the compositional function, the domain of changes. Okay, so in our previous example here, our domain didn't change, and that's because of the nature of how polynomial functions work. The domain is consistent for both g and f. But you see here that we already noticed that domains for these functions are different. So that already gives us a key and a clue in that our domain is going to be slightly altered for our compositional function. So let's do our compositional function here, okay? So f of g of x, right? So I'm going to use my kind of method of ascertaining it, which is include these empty brackets where you would plug in your inside function, right? So you have g here and g here. So that looks like g of x minus 3 divided by g of x. All right, so if we were to plug in g of x, we get 5x minus 7, hopefully, divided by 5x minus 4. And in question number 3, I think, we covered that the domain of a rational function is all the real values except for when the denominator is equal to 0. So we're going to find that special case. So we're going to set 5x minus 4 to be equal to 0, and we get x equals 4 over 5. So that means that the domain of f of g of x is going to be x belongs to all real values, but x cannot equal 4 divided by 5. Okay, so we can see that by applying the compositional function here, our domain is totally and entirely different than our two independent functions, the domains of our two independent functions here. All right, so that's a case where the domains are different. So the junior tutor goes on to give us the reasoning on how we solve question number 6. Wait, no, question number 2. So they go on with the reasoning of how to solve how to find the domain of a rational function. But we've already been through that, so we don't really need to cover that too much. I'm just going to read it quickly to make sure that they are correct here. And yep, this is correct. So this solution is correct. Good work. Cool. All right, so question number 9. So the question reads, what is the remainder when 3x to the power of 4 plus 2x cubed minus x squared plus 2x minus 19 divided by x plus 2? So this is what we call long division. I covered previously there's a technique called synthetic division. I probably will cover that too here. But basically, the remainder of this quotient helps to signify that the divisor itself is not a factor of the division, right? So long division is basically a way to check whether or not that the divisor is a possible factor of this polynomial. When you get to larger polynomials, so anything greater than 4 or 5, or 6, when you get up to those numbers, it's really hard to factor them manually. So you can use a different technique by guessing or extrapolating the factor and then using long division to figure out whether or not it is a factor. It is indeed a factor. Okay. So here is telling us that there is a remainder, right? So usually in normal division, whenever you have a remainder, it's a fraction, right? It's the remainder over the divisor itself, right? In this case, it is the same thing. So we're going to find the remainder for this long division through long division, okay? So first of all, I'm going to draw a big divisional bracket here. We're going to put in our polynomial, okay? Okay, and then we're going to put our divisor here, or the possible factor. Okay, so basically how to divide is by treating these as the digits of a number and trying to simplify them as we go. So we see here that we have a 2-digit number or a 2-term factor here. So we're going to try to get rid of 2 digits at a time here. Okay, that's how you kind of think about it. It's easier to just do the example. So how do we get rid of 3x to the power of 4? So we can multiply our factor by 3x cubed. Okay, so let's multiply it by 3x cubed. So if we multiply this by 3x cubed, we're going to get 3x to the power of 4 plus 6x cubed. Okay, all right, so as always, we subtract these, and we got rid of our first big digit, right? So this is equal to 0, and this is equal to negative 4x cubed. All right, we're going to move down our next digit, or our next term here, as negative x squared. So how do we get rid of negative 4x cubed? We can multiply it by negative 4x squared. Okay, so we multiply this by negative 4x squared, we get negative 4x cubed. Oh, that's a 2. Minus 8x squared. If we subtract this, negative is positive, so this equals to 0, and this equals to 7x squared. Just want to make sure I'm not messing anything up here. All right, next, we move down to our next term. All right, plus 2x. So how do we get rid of this? We can multiply it by 7x. All right, so if we do that, we get 7x squared plus 14x. Subtract, we get, oh, that line was bad. We get negative 12x minus 19. We're almost there. So how do we get rid of the negative 12x? We can multiply it by negative 12 itself. You get negative 12x minus 24. If we subtract these together, we get 5. So our remainder here is basically 5. So remainder equals 5. All right, so this is one way you can do it. The other way is through synthetic division, and I'll go through that now. So the way synthetic division works is you take the coefficients of your polynomial, of your dividend, and you'll take the solution to this factor. So in this case, x plus 2, so the 0 for this is negative 2, or the solution is negative 2. So we're going to take the solution, we're going to write it out like here, and we're going to have an upside down division bracket, okay? And we're going to write the coefficients of our polynomial, which is 3, 2, negative 1, 2, and negative 19, okay? And what we're going to do here is we're going to take our first coefficient, move it down, and multiply negative 2 by it, and add it to our second one, and move that one down, okay? So if we move it down here, we get 3, and we're going to multiply this to negative 2 times 3, and we're going to add it to this, okay? So we're going to add negative 6 to 2, and we're going to get 4, all right? So I'm just going to illustrate it once, and then I'm going to do the rest, because it's going to get messy. So we multiply this, which equals negative 6, and then we're going to move it up here, and we're going to add it to this, right? So we're going to add negative 4 to this, okay? So if we do that, we get negative 2. Sorry, we subtract them together. Negative 2, negative 6. So we get, why am I saying 4 here? This should be negative 6. Sorry about that. This should be negative 6. So that if we do the addition for this, we get negative 4. Negative 4 times negative 2 is 8. 8 plus negative 1 is 7. 7 times negative 2 is negative 14. Plus 2 is negative 12. And then finally, we get negative 12 times negative 2, which is 24. 24 plus negative 19 is 5. Okay, so how do we read this now? So the last digit that we get is going to be our remainder. So if this digit is equal to 0, then we know that this is a solution, or this is a 0 to our polynomial. But if we have a remainder here, then this is in fact not a solution. Okay, so this is our remainder. So we'll just box this off and label it to be equal to r. And these coefficients here are the coefficients of the resultant dividend, or the quotient, sorry. And the quotient has 1 degree less for the polynomial. So the quotient is, in fact, so this is going to, if this is x cubed here, then this first place, this first digit here is going to be x squared, and so on and so forth. So this is x squared, this is going to be x, this is x, this is going to be the coefficient c, and so on and so forth. So this is x to the power 4, x cubed, x squared, and x, and this is c. Then this is going to be x cubed, x squared, x, and the coefficient itself. Okay, so that's how you read it. And if I did it all correctly, then these two should be the same, because these are just two different methods of finding the same answer. Okay, so the remainder is 5, and we did this through long division and synthetic division. So the solution is correct. All right. Finally, let's move on to the last question of the day. So the last question of the day is, how do you factor x cubed minus 27? So we're going to use the sum of cubes to find the factor for this, to factor this. So the sum of cubes basically reads, is a rule of how to factor polynomials of form x cubed minus y cubed, or plus or minus, okay? So the sum of cubes helps us to factor this into its appropriate factors. And there's two different rules. So when you have x cubed plus y cubed, this can be factored to x plus y times x squared minus x times y plus y squared. Okay, so that's for x cubed plus y cubed. The second, I guess, rule is when you have x cubed minus y cubed. Right? If you have x cubed minus y cubed, then you can factor it like this: x minus y times x squared plus x times y plus y squared. Okay. So so the x and y can be numbers, it can be variables, but that's how you factor it. Okay. So the first thing that we need to do when we look at our factor here is that we notice that there's a power of a cube here, right? So the second criteria is we need to know if the second term here can also be written as a power of cubes. And in fact, it can. So x cubed minus 27 can be written as x cubed minus 3 cubed. Okay, so now that we have this, and we can clearly see that we can use the sum of cubes to factor this, we use our second rule here, and we can write it out as x minus 3 times x squared plus 3x plus 9. Okay, so that's how you use the sum of cubes to factor any cubic polynomials. But that's pretty much it. Okay, so that's how you factor cubic roots, not cubic roots, cubic polynomials, I guess you can say. And the junior tutor got it correct. So the solution is correct. Good. Cool. All right. So that wraps up today's lesson. I covered 10 questions surrounding algebra functions and compositional functions. If you have any other issues or any other problems with your homework, tests, or assignments, please submit them to OneClass, and we'll get to them as soon as possible. And I hope you guys learned something today. Other than that, I wish you guys a good afternoon, and I'll see you guys